It is.
Your hair's so much longer now.
It is. It was almost 8 inches longer than this before I got it chopped off. So that was a couple months ago. It was getting way too warm and way too heavy. I was just getting headaches all the time by just existing with my hair. Yeah. We have 2 chapters left to cover. It doesn't really matter that much what order we cover them in. We'll cover them in the order that the syllabus tells us to. So chapter 20 is going to come before chapter 19. We have to learn about carbohydrates now. All right. Check-ins should not exist anymore. I have no idea why they're still there.
Yeah, they're just there.
And they're working now.
I deleted them once. I have no idea why they're still around. I will delete them again.
3 points.
But that they're documents.
Does it
Yeah.
actually count?
Yeah.
Oh, it does. Oh.
The mind is shows that.
The check-ins will not affect your grade. I promise you.
Yeah.
That's good.
Yeah, they won't affect your grade. I told you not to do them. Don't do them, please.
Please.
Okay, so we have seen some carbohydrates in the lab already. Carbohydrates have a bunch of alcohol functional groups in them, and then either an aldehyde or a ketone. All right. These are all carbohydrates that have only one carbon chain in them. We call those monosaccharides. If we join multiple monosaccharides together through an oxygen linkage, all right, then we call those polysaccharides. There are special-ish names for polysaccharides that are between 2 and 8 individual carbon chains long. So 2 of those monosaccharides joined together, it's called a disaccharide. All right. Anything bigger than that, we normally refer to as an oligosaccharide. Oligo. So oligo just means a few of the monomers put together. All right. Here you can see a common disaccharide that tends to give me indigestion. That's lactose. Most adults are, at least to some extent, lactose intolerant. If you can eat a giant bowl of ice cream and suffer no consequence for that, then that's awesome. All right, it's good to be you. Does anybody know why most adults are lactose intolerant?
Has to do with the enzyme.
Yep. You know what the enzyme's called? Lactase. Yeah. If you have to have a guess at an enzyme, like put something fancy in front of the suffix ase, and you're probably really close.
Yeah.
All right. So the enzyme that cleaves lactose into its 2 parts, which are glucose and galactose, is the lactase enzyme. Adults don't really make very much of that enzyme anymore because they're not normally drinking lots of milk. All right. So they end up not being able to process this, and it causes digestive issues.
Can you ingest lactase from like?
Yep.
Okay, that's what I thought.
As a matter of fact, most of the commercial products that yeah, are literally like a dose of lactase enzyme.
So you drink the milk, but it also has lactase.
There also are forms of milk where the lactose has been replaced with other stuff or already pre-digested. Yeah.
Do you like have a little bit of tolerance to just constantly drinking milk?
I don't know. Yeah, I don't know. So here is an example of a polysaccharide. This is starch. All right, starch is a bunch of glucoses bound to one another. It turns out that most of the carbon-based biomass on Earth is also a polymer of glucose. It just so happens to be one that humans cannot digest very well or at all. Anybody know what polymer of glucose? So what do you see a lot around you everywhere you look?
Cellulose.
Plants, right? And plants use cellulose as their structural polymer. It turns out that lots of organisms can digest cellulose and break the chemical bonds between the glucose units to access that as a caloric form of glucose that they can use. All right, grass is incredibly nutritionally dense if you can digest cellulose. That's how cows can stand in a field and eat grass and get enormous, right? Humans, when we eat salad, we don't get enormous. We do that when we want to reverse being enormous. All right. And the reason why is because most of the biomass in salad is cellulose. In other words, it's calorically completely unavailable to us. We consider that to be fiber, just undigestible stuff that runs through our digestive system. All right. Fiber is also important, by the way. It acts kind of like a scrub brush for your intestines. So carbohydrates are synthesized by plants in the process that we call photosynthesis. Here's the most common balanced chemical equation for that. All right. So lots of plants make glucose and then store it how? In what polymer? Cellulose. Good. Now, monosaccharides, although glucose has 6 carbons in it, not all monosaccharides do. All right. Monosaccharides, generally speaking, are 3 to 6 carbons big, at least the ones that are made biologically. So if we think about it, it's pretty easy for us to see what the simplest 3 carbon monosaccharides might look like. So let's take a look at those for a second. All right, remember that every monosaccharide has to have either an aldehyde or a ketone, and then the other carbons have OH groups on them. So if we had a 3 carbon sugar that had a ketone in the middle carbon and an OH group on the other 2 carbons, that's a carbohydrate. All right, the simplest 3 carbon monosaccharide that has a ketone functional group. So monosaccharides or any sugars that have a ketone functional group are called ketose sugars. Now, if we had a 3 carbon monosaccharide where the first carbon was an aldehyde, and then carbons 2 and 3 had OH groups, that would be the smallest possible aldose sugar. So aldose sugars are sugars that have aldehydes. If you prefer condensed structures to bond line drawings, here are the condensed forms of those 2 structures. All right, so the smallest ketose sugar that we could possibly get is, the common name for it is dihydroxyacetone. Looks like acetone with a couple of extra alcohol functional groups attached to it. And then glyceraldehyde is our 3 carbon aldose sugar. Note that both of them are constitutional isomers. All right. We see that in a great many of the sugars of the same number of carbons. For example, glucose is an aldose sugar. Fructose is a ketose sugar, but they have the exact same chemical formula. All right. They are constitutional isomers of one another. We'll take a look at those. It's a little more complex than these because they're 6 carbons big instead of 3. You don't have to remember these, but we do have nicknames for those types of sugars depending on how many carbons they have. The prefixes should make sense if you've been paying attention so far. All right. And we could use both the aldose slash ketose thing and the number of sugars, or sorry, the number of carbons to give a pretty good descriptor for what kind of a sugar we're talking about. So for example, glucose is a 6-carbon sugar that is an aldose sugar. So we would call glucose an aldohexose. Does that make sense? That's not on the exam. How do I know it's not on the exam? It's not in the study guide. All right. Yeah. Hopefully you're convinced that the study guide is important by now. I'm going to quit talking about it. Carbohydrates, because they have lots of OH groups, they all are very soluble in water, at least the small ones. All right. They have high melting points because they have strong intermolecular forces, and the monosaccharides tend to taste sweet. They don't all taste as sweet as one another, but they all taste pretty sweet. They're all very, very water soluble. So the interesting thing for scientists who study carbohydrates is that they are packing lots of places for stereochemistry into a very, very small space. So the way I want you to look at this is that this carbon right here, because it has 4 different things attached to it, the CHO, the OH, the H, and the CH2OH, those are 4 different groups attached to that central carbon. Anytime we have that kind of a carbon with 4 different things attached to it, there are possibilities for 2 different ways for that carbon to occupy space. In other words, because there's only one of those carbons in this molecule, there are 2 ways for this molecule to occupy space. These are a pair of stereoisomers. All right. For a hexose like glucose, let's take a look at glucose for a second. We'll just draw it. So there's our first carbon, the aldehyde carbon for glucose. And from there, this is going to be our carbon 2. This is going to be our carbon 3. That will be our carbon 4. This will be our carbon 5. And then we'll have a CH2OH at carbon 6. Now, what happens in between? All right. It turns out that the most common form of glucose used in living organisms has the other groups attached to the carbons like this. The OH groups go right, left, right, right. Each one of these 4 different places is a place where there are 2 options for where to put the OH and the H.
Would that mean that it has 8 forms?
Glucose only has 2 forms. All right. So this is D-glucose. The mirror image of D-glucose is also glucose, but it is the L version of glucose. So the mirror image has all of those individual carbons mirrored what they would be normally. So instead of right, left, right, right, we have left, right, left, left.
So the bottom left one is just supposed to be H on the first and the B.
Oh, that should be an
Is
H.
that right? Okay. That was,
Sorry, I did not mean to write that.
that's okay.
You see how these are mirror images of one another? This right here in the middle is the mirror plane where you reflect one onto the other. They're not identical. They are literally mirror images. The same way that your left hand and your right hand look incredibly similar, unless you've had a disfiguring accident. All right. But they are not identical to one another. We can't take this one and turn it into a right hand. They're never going to be the same. All right. They're mirror images of one another. These molecules are mirror images of one another as well. It turns out that D-glucose, the D version of the sugar, is the one that is used in almost all biochemical processes. Why? I have no idea.
What is the L-glucose?
What is that?
What is the L-glucose?
Not much. There are a small number of organisms that could metabolize it and use it, but it is not a normal part of like blood sugar for any organism. Like D-glucose is the glucose that gets circulated in us to hold our blood sugar steady.
Okay.
All right. There are very few organisms that use the L versions of the monosaccharides. Why? Again, no idea, but it's true.
It's true. I don't understand how they're not the same, because aren't they technically still stereoisomers?
Well, stereoisomers are not identical to one another. So that would be like claiming that this molecule and this molecule are identical to one another. They're not. And the reason why is because they inhabit space differently from one another, right? So you saying that this and this are identical is like saying that your left hand could fit into a left-handed glove or a right-handed glove. All right? They occupy space differently from one another.
But they do the same things.
Not really. By doing the same things, can L-glucose function as blood sugar in a human? No. Our enzymes cannot recognize L-glucose. It doesn't fit those enzymes. So enzymes have an active site, a place that they use to hold their reactants and change them into products. And that active site is designed to fit a specific shape. If we have a molecule that is the mirror image of that shape, it's not going to fit in that enzyme anymore, right? So our enzymes are all developed to use D-glucose to fit that shape. The mirror image of that shape doesn't fit our enzymes. We can't use it. Does that make sense?
Yeah, so kind of like the glove thing, right? Like it wouldn't fit.
It wouldn't fit. You're probably too young to remember this, but there's a joke that goes along with that from the O.J. Simpson trial. Do you remember it?
You can't commit.
Yeah. If the glove does not fit, you must acquit. Yeah.
Oh, and then
That was he did end up in jail anyway. But that trial was like, at that time, it was the trial of the century. Like, I was in high school and we took days out of our US history class to like watch the OJ trial.
My parents talked about that. They were like, yeah, we would have times where we would just stop doing what we were doing and like watch it. And then it was like a beefed up version of like Amber Heard and like Johnny Depp. Like that's how
Johnny Depp was a pretty big deal too.
Right.
A lot of people like watched that. And then I don't know, every trial is called the trial of the century. Like what was the girl who Casey Anthony? Do you remember the one that probably killed her daughter and like stuffed her someplace? Everybody watched that trial too. So I don't know what the next trial of the century is going to be.
the Murdoch trial.
Yeah,
It just happened.
It's over, right? Yeah, it's over.
It just ended.
That wasn't much of a trial of the century. Like they took like the jury like went and took a smoke break and like
I
Dang
mean, yeah,
it.
it was, but it's so interesting to hear the whole backstory. Like,
Yeah.
everyone thought it was hard.
It's a writing time.
so there are only two possible enantiomers. So enantiomers are a pair of stereoisomers that are mirror images of one another. That's an important term for you to remember. All right. Stereoisomers that are mirror images of one another are called enantiomers. So D and L glucose are the two enantiomers of glucose. Does that make sense? Okay. So enantiomer is just a term for, it's actually denoting a relationship between two things. The pair of enantiomers are the two mirror images of a given molecule. Now, how do we know whether our monosaccharide is a D monosaccharide or an L monosaccharide? What it has to do with is the furthest stereocenter down on the carbon chain. The one farthest away from the aldehyde or the ketone. Now here, there's only one. And on that stereocenter, the OH group is pointing to the right. This is the D version. Okay, so if we look at D and L glucose that we just drew a minute ago, at the farthest carbon down that has a stereocenter right here, the one furthest away from the aldehyde, the OH group is pointing to the right on D glucose. All right. And on L glucose, that OH group is pointing to the left. So we're always looking at whatever the farthest stereocenter away from the aldehyde or ketone is to determine whether it's D or L. And it makes sense because L is like the OH group is on the left. Does that make sense? L left.
Something.
D and L actually stands for dextrorotatory and levorotatory. So originally, the way that we classified the difference between enantiomers is if we have that enantiomer in solution and we shine polarized light through that solution, if we only have one enantiomer in there, the polarized light, the plane at which we shine it, actually gets rotated. All right. So when we shine the light through that sample, the light comes out at a slightly different plane than it did going in. And it turns out that D glucose rotates the light rightward, clockwise, and L glucose rotates the light counterclockwise. So dextrorotatory and levo for left. Yeah. You asked D and L. That's how those prefixes show up. All right. It's when we put those things in solution, which direction do they rotate plane polarized light? So glucose has 4 of those stereocenters. How many possible ways could we draw a molecule with 4 stereocenters? More than that. It's 2 times 2, which is 4, times 2, which is 8, times 2. Yeah, 16 different possibilities. Because we have 4 different choices to make, right? Left or right for each one of those 4 possibilities. And just like we talked about in our drawings, it's always the chiral center, the stereocenter that is furthest away from the aldehyde or ketone that decides whether our sugar is a D sugar or an L sugar. Just like we said earlier, all the natural sugars are the D versions. Again, why? No idea. Why is it that 99.99% of the alpha helices that we run into in proteins are right-handed helices? No freaking clue, but it's true. All right. Why is it that the DNA double helix is a right-handed double helix? I don't know. I'm left-handed. It sure seems like the entire universe is conspiring against me at this point, but I don't know.
Possible to be both.
What's that?
Possible to be right.
Ambidextrous. So D glucose and dextrose is often given as a common name, not for glucose in general, but for D glucose. Remember, it is dextrorotatory, right? So that's why we give this the common name dextrose, because that sort of like signifies that's the D version of glucose we're talking about. It is the most abundant monosaccharide. So most organisms use some kind of polymer of glucose to function. Who cares what normal blood glucose levels are unless you are like going into nursing and need to memorize that for the TEAS test or something? What's that? 80 to 120 is normal?
It's 71.
Oh, is that an outdated?
Maybe, my son's diabetic, they tell us to be
Okay. Maybe it's not outdated now. We've just like shifted the normal window because people eat so much sugar that their blood sugar levels tend to be higher on average.
Could be because he's younger too.
If you have too much glucose in your blood, you end up storing it as glycogen. So glycogen is a normal storage polymer for us. It's like our quick store of energy. Our long-term storage for glucose is in fat. All right. It takes a lot more metabolism to turn our glucose into fatty acids, but we can do it. All right. And that is how we store more energy for long-term storage. And then insulin, remember insulin was what kind of molecule? We learned about it in the proteins chapter. So it was well, it's not just an amino acid. It's a small, you could call it a peptide or a small protein. All right. Remember, it had two different chains that were required in order for it to do its job. And those two chains were held together by what kinds of interactions? Well, there are hydrogen bonds between the two strands, but there are covalent bonds too. How do we covalently bond two different peptides together?
Electrostatic interaction.
How do we covalently bond two individual peptides together? Disulfide linkages. All right. I'm just trying to help remind you about some stuff that we covered from the earlier chapters. So insulin has some disulfide linkages that allow the two peptides to stay together. And insulin is a signal. All right. It's a signal that allows us to regulate whether we're making glycogen or whether we're breaking glycogen down to make glucose, depending on whether our body needs energy or whether we have enough. All right. And there are lots of reasons for not producing enough insulin. Some people just don't produce enough genetically, so they end up with diabetes. Or if you end up basically wearing out your ability to make insulin because you are eating lots of sugar all the time, then you can develop diabetes all on your own too. All right. For people that are like on the edge of developing diabetes, there's actually like an alternative mechanism for producing more insulin. You get like quite a good shot of insulin by just doing vigorous exercise. So that's one of the things that they tell people that are like pre-diabetic, which means that they're starting to not produce sufficient insulin by themselves anymore. Exercise, that will help fix that problem.
That will help fix type 2, not type 1.
Not type 1.
Yeah.
Type 1 is you genetically can't make insulin the way you're supposed to. You're screwed. Yeah. Yeah. We need to give you insulin because you cannot make it. Now, in the long run, maybe we will develop some sort of gene editing technology like CRISPR, all right, to be able to repair defective genes in people that have type 1 diabetes, where they can, I mean, maybe they don't have a pancreas anymore. That'd be really bad, all right? But if they have a pancreas and it's just not working to make insulin the way it's supposed to, maybe that's a problem we can fix in another 50 years. That'd be pretty freaking sweet.
Yeah. They did a transplant, I think there's a transplant a couple years ago.
Transplants are also problematic, right? If you have a transplanted organ, you got to take anti-rejection medication for the rest of your life. That's not so great. I didn't know about this until we had a cat that we were seriously considering giving a kidney transplant to, which basically you do that by adopting a shelter cat and stealing one of its kidneys, and then you take care of both cats.
Oh, really?
Cats only need one kidney to get by, and for some reason, cats don't have the same problems with rejecting organs that humans do. Like cats are happy to have whatever kidney you give them, and they're fine. Isn't that awesome?
I'm looking at my nanny.
It's all right. Yeah. So let's take a look at a couple of different monosaccharides. These are all hexoses. They've got 6 carbons in them. All right. Glucose and galactose here. Those are the two monosaccharides that link together to form lactose. All right. They are both what kind of sugar? Based on that CHO. That's an aldehyde, by the way. Aldose sugars, right? And you can see fructose instead has a ketone functional group. It is a ketose sugar. So whereas lacking lactase enzyme is bad enough to give you indigestion, people that lack the enzyme to metabolize galactose, they end up having all sorts of much more severe problems than just indigestion from that. All right. So a lot of disaccharides are very common metabolites that we are digesting constantly. People that lack some of the enzymes to do that end up with very serious problems. And I would bet that there is probably a commercial drug that is just that enzyme in a freeze-dried form for people that have this condition. Sucrose, common table sugar, is a disaccharide that has glucose and fructose together. It's probably the sweetest out of all the disaccharides. All right. Have you guys ever tasted just plain glucose all by itself?
Yeah, I think they give that to you when you're like pregnant.
Oh,
That's yeah.
The glucose drinks are also used a lot of times as if you're having they're used to settle your stomach. All right. If you have an upset stomach, a lot of times, yeah, drinking some.
Yeah. I think
Does it?
it's-
I've never been pregnant before, so I can't.
Those one drinks, the honey,
Yeah.
little barreling or.
The barrel.
I remember those. I remember those. So fructose is just half of sucrose. It is the major, not the only, but the major sweetening component that's in honey. And if you wonder why honey might be a better sweetener to use than regular table sugar, it's almost twice as sweet as regular table sugar is. All right. Or sucrose is, sorry. Fructose is almost twice as sweet per unit mass as sucrose is, which means that if you are comfortable with the flavor of honey instead of table sugar, you only end up needing about half of the mass of total sugar in your coffee or in your tea or in your whatever, right? Pretty neat. So if you're trying to save a few calories, honey instead of sucrose might be a way to do that if you like the flavor just as well.
So what's in stevia?
Stevia is a well, yes, it's non-nutritive, but I don't think it's actually, I'm struggling to remember whether the compound that produces sweetness in stevia leaves is actually a carbohydrate or not. All right. There are some sweeteners that are actually sort of like peptide based instead, but they just trick our taste receptors into tasting sweet. I'm not sure off the top of my head which one stevia is. All right. Equal is a version of, is it Equal or is it Splenda? All right. Splenda looks almost identical to sucrose, except for a couple of the OH groups have been replaced with chlorine atoms instead. That small difference is enough that your body can no longer do anything metabolic to Splenda. All right. Your taste buds can taste it and it binds in the same place that sucrose does and produces the same sensation. But your body can't metabolize it anymore.
That's probably why it's got that aftertaste, right?
I don't know.
Splenda's got a weird aftertaste.
Does it?
Yeah.
I can't.
Stevia kinda-
I'm lucky when it comes to artificial sweeteners. They all taste good to me.
It tastes like
Yeah.
plastic. It's gross. That would be.
Here is one of the hard parts of this chapter that we have to think about, that we have to reckon with. All right. We have not talked much about this type of chemical reaction yet. So what happens, generally speaking, when we react an alcohol and an aldehyde or a ketone? We get an acetal. All right. Let's remind ourselves of that kind of reaction. So for example, if we had this ketone and reacted it with a couple of methanols, and that normally requires some kind of acid catalyst because we're not talking about inside the body anymore. Now imagine that we had a ketone and an alcohol on the exact same molecule. If we use acid catalysis here, note what's happened in this reaction up here. That oxygen has formed a new bond to that carbon. And then it's happened again a second time with the second one of those OHs. So same thing is going to happen here. This oxygen is going to end up forming a new bond to that carbon. We don't have another oxygen around here to completely kick out this oxygen. So instead, what happens is it becomes an OH group. So if we form a new bond between this oxygen and that carbon, how many atoms are we going to have in that ring total? 5. All right. 1, 2, 3, 4, 5. So let's see what that looks like. The other things that are left at this carbon are a methyl group here, and then whatever this oxygen is after the bond from this oxygen forms. It turns out that this oxygen turns into an alcohol. So the functional group that we get when we put a single alcohol together with an aldehyde or a ketone is sort of like halfway to an acetal. So we call that kind of functional group where we have what looks like an ether and an OH group on the same carbon. We call that a hemiacetal. Why do we worry about hemiacetals? Because hexoses make hemiacetals with themselves a lot. Let's take a look at an example. Here again, is the structure of D-glucose. It turns out that when D-glucose forms a ring with itself, the ring ends up being 6 atoms big. 6 atoms big. So let's count from the aldehyde. We know that that's going to be the first atom in the ring. Which OH group would be the one that is used to make that bond to this carbon right here? Remember, there are going to be 6 total atoms in the ring. So let's count. 1, 2, 3, 4, 5, 6. That oxygen right there is the 6th atom in the ring. So 1, 2, 3, 4, 5, 6. Now, the really cool thing is that we can draw a version of D-glucose that shows where the correct side of the ring all of the hydrogens and oxygens are on. And it's not even really that hard to do. All right, so let's do it. The first thing that I'm going to do is literally take this picture and turn it 90 degrees from where it is right now. In other words, I'm going to draw it so that the aldehyde part is pointing to the right. Go ahead and redraw it. 90 degrees twisted from where it is right now. By the way, this sort of projection where we show the stereochemistry at each one of these carbons is called a Fisher projection. Can I remember if there's a C in that spelling somewhere? All right, if we turn this 90 degrees from where it was, good so far?
Honestly, does it matter if the age is at the bottom or-
It does. When we turn this over, this H that was on the left has to be on top here. What's that?
for the al-
You mean for the aldehyde over here?
the al-
Doesn't matter. Yeah, it doesn't matter. As long as we have a double bond to an oxygen and a single bond to a hydrogen on that carbon, we're good. All right, doesn't matter whether it's top or bottom. So we know that 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6. That oxygen right there is going to end up making a bond to that carbon right there, the aldehyde carbon. So what we are going to do now is we are going to sort of take this molecule and bend it backward like this, so that this oxygen is going to be really close to that carbon. All right. And when I do that bending, I'm going to make sure that the H's and OH's stay on the same side or on the same top or bottom as they were before. So there's carbon 1, here's carbon 2, which means my hydrogen there is going to be up and my OH group is going to be down. And at carbon 3 next door here, my OH group is going to be up and my hydrogen is going to be down. And at carbon 4, 1, 2, 3, 4, which will look right here, where are my hydrogen and OH? 1, 2, 3, 4. The hydrogen here is going to be up and the OH is going to be down. At carbon 5, things are going to look a little crazy because we are going to have our OH group pointing straight over to have it next to where the aldehyde is. So what other things do we have attached to this carbon other than the OH group? A hydrogen and so we're talking about the things bound to this carbon right here. All right. We've got an OH, a hydrogen, and a CH2OH, right? So we need to know whether the CH2OH and the hydrogen are on top and bottom or bottom and top, respectively. It turns out that with D sugars, the CH2OH always ends up, and the hydrogen ends up down. We are really close to drawing a full cyclic version of glucose now. all we have to do is realize that this oxygen is going to make a bond to this carbon now. All right. And when that oxygen makes that bond to this carbon, we are going to turn this oxygen into an OH group. So let's do it. So what other two things are going to be attached at this carbon besides the OH and this other carbon, or besides this oxygen and this other carbon? What other things are we going to have here? We're going to have a hydrogen that was there when it was an aldehyde, and we're going to have an OH group. Now, it turns out that when this oxygen makes its bond to this carbon right here, whatever side the oxygen attacks from to make that bond, the OH group is going to end up on the opposite side of that, which means this is a possible outcome of the reaction. We could have the OH group here pointed down, or we could have the version of cyclic glucose where the OH group is pointed up instead. Either one of those is a possible outcome of when glucose decides to make a ring with itself. So we see that all of the information from these carbons, whether the H and OH were on the top or the bottom, is still there once glucose makes a ring with itself. All right. The only place where we lose that information is at this carbon right here, because when we form that bond, the resulting OH group could end up on the top or the bottom then. So it turns out that when our OH group is pointed down and the CH2OH is pointed up, we call that the alpha anomer of glucose. And when the OH group and the CH2 or the CH2OH are pointed up, we call that the beta anomer of glucose. These are both cyclic versions of glucose.
So is that a hemiacetal?
Yes, these are both hemiacetals. So if we look at that functional group, it's like an ether on one side and an OH group also, right? That's a hemiacetal. Hemiacetals are basically a hidden version of an aldehyde or a ketone. How do we know that this was a hidden aldehyde and not a hidden ketone? Well, because there's also an H present on that same carbon. Remember when we talked about Benedict's reagent? So finding reducing sugars. Sometimes reducing sugars don't look like they have an aldehyde because it's hidden as a hemiacetal. All right. That's some of the chemistry that we needed a little bit longer to go back over again.
So then what would be different with like?
How would that look when we cyclized it? Well, I'm glad you asked. We can do that. Okay. So let's take a look now at D-fructose instead. If you remember the structure of D-glucose, which you don't have to for us, all right? I don't expect you to memorize these structures, but D-fructose is very, very similar. At carbon 1 of D-fructose, we have a CH2OH. At carbon 2, we have a ketone functional group. And then after that, the other carbons are identical 2, 3, 4, 5. I made it too long. So the last 4 carbons of D-fructose are identical to the last 4 carbons of D-glucose. Everybody see that? It turns out that D-fructose prefers to form a ring with 5 atoms in it instead of 6. All right. It is possible for D-glucose to form a 5-membered ring. It is possible for D-fructose to form a 6-membered ring. They are not a major component of what we see of glucose and fructose in blood sugar or other places. Right? So when fructose forms a ring, it's normally a 5-membered ring. Which OH group would be the OH group that we are using to form the 5-membered ring by binding to the ketone carbon? Let's count. 1, 2, 3, 4, 5. That oxygen right there is the one that we're going to use to form that bond. So let's see what D-fructose looks like in its cyclic form. All right. I am going to rotate D-fructose by 90 degrees and draw it again. This oxygen and that carbon are going to end up bound to one another in the cyclic form of D-fructose. That oxygen and that carbon are going to end up bound to one another. So what we're going to do now is we're going to twist the ends of this molecule to get those 2 atoms closer to one another. All right. There's carbon 1. And at carbon 2, we want to maintain the same side of the molecule for the OH and the H as we have in the molecule when it's written up here, turned sideways. So the OH is going to be on the top side at carbon 2 and the H on the bottom side. Sorry, that's carbon 3. And at carbon 4, the H is going to be on top and the OH on the bottom. Carbon 5 is weird because our OH is already pointed over toward the atom that it's going to end up binding to. So we're left with an H and a CH2OH. For D sugars, the H is down and the CH2OH is up. So that is what D-fructose looks like right before we form that new bond between that oxygen and that ketone carbon. This ketone oxygen is going to become an OH group when we form that hemiacetal. But depending on whether this OH group attacks from the bottom side of the ketone or from the top side of the ketone, we could end up with 2 different possibilities for what this carbon right here looks like. All right. So one of those possibilities has the OH group pointed up and the CH2OH pointed down at carbon number 1, or I guess at carbon number 2. I've done a very poor job of space management here. So we would call this, which anomer of fructose would we call this if the OH group and the CH2OH group are on the same side? They're both on the top of the ring. The alpha anomer was when the OH group here was on the opposite side of the CH2OH group.
So that's beta.
This is the beta anomer. And if we just redrew this, but had the CH2OH up here and the OH down here, whoa, you can't even see what I'm pointing at. If we redrew the beta anomer, but had the CH2OH up here and the OH down here, that's what the alpha anomer would look like. So I'll draw it over here and actually give it enough space that it doesn't look like garbage. There is the alpha anomer of cyclic fructose. So a 5-atom ring with an oxygen in it is called a furan ring, F-U-R-A-N, furan. And because of that, we would call this, if we were naming it as closely as we possibly could, we would call this alpha D fructofuranose. In other words, fructose folded into a 5-membered ring in its alpha anomer.
Didn't just use like pentose to say that it needs a 5.
But that doesn't tell us about whether the H and OH groups are pointing up or down. So, for example, if I was naming this thing right here, the alpha anomer of glucose,
Yeah.
all right? A 6-membered ring with an oxygen in it is called a pyran ring, P-Y-R-A-N. So if I was naming this, I would name it, I'm trying to find space to name it here, all right? I would name this thing alpha D glucopyranose. Now, why not alpha D hexopyranose?
That's what I was asking.
All right. And the reason why is because not every hexose has carbon 2's OH group pointing down and its H pointing up. And not every hexose has carbon 3's OH group pointing up and hydrogen pointing down. Only glucose does that.
So they decided to just not do alpha D hexoglucose or something like that, and come up with a different word.
Well, if we were cyclizing galactose instead of glucose, then it would be alpha D galactopyranose.
Yeah. They just don't want to say hexo word.
Hexo is not a specific name that points to specific sugar that is cyclizing. A hexose is just a 6-carbon sugar. It could refer to any one of a bunch of different 6-carbon sugars.
Yeah.
Can I see the name for the?
We will practice drawing cyclic forms of monosaccharides again next time we're together, because it's not easy. All right. But the stepwise way to do it by tilting it 90 degrees and then folding it, that's the easiest way I know of to teach it. All right. Once you know what a 5-membered ring looks like in a sugar, then it's easier to get to this place because you know it's gonna end up looking like this afterward. All right, so imagine what it's gonna look like when it's done, and then when you're folding it, make it look almost done. Does that make sense? We'll practice that more next time we're together. You guys have a weekend to like mull it over before then. Okay? We'll probably even be able to practice that some next, wait a second, next Tuesday, because I don't think that our chem tests for the things that we made in lab will take a full 2 hours. All right, we should have some time to practice this some more on Tuesday.
We're just still final.
Yeah, that's a good question. No idea.
Are you gonna make it?
During finals week.
Are you gonna make us go clear to the 17th?
During finals. Okay, we're doing great on time right now. There's no reason we couldn't have it on Tuesday at finals. We could also have a final exam study session on Tuesday and then do it on Thursday at finals. All right, so I'm game for whatever, but I'm seeing good things in terms of where we're at pace. We have plenty of time to finish.
Yeah, but
Limits.
learn more about repression than I did probably the last. Now I know.
Ghost energy drink,
Yeah.
is it good? Can I see the ingredients?
It tastes really good, actually.
It is, those are really good.
Naturally, the chemist likes something.
A lot of caffeine, 200 milligrams.
It's not much of a bag.
Thanks. I can't.
Have you seen this? You know, it's like-
That's exactly how you work.
Yeah.
Do you want to
It's
probably
like-
I'm just.
So these.
There are some people whose blood pressures are not affected very much by caffeine. I'm not one of
But
those.
when I do,
Forever until I start working.
product and then I'll do. Yeah. No one like 170.
Have a